Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So for part number 2, we will start our discussion with dry and atmospheric air. Okay, in air conditioning application, we will consider two types of air. First, we will consider dry air, and the second one is the atmospheric air. So as we know, in terms of composition, our air consists of first 78% nitrogen gas, 20.9% oxygen gas, and the rest 1.1% consists of different type of gases such as neon, argon, krypton, and also carbon dioxide, plus H2O. And this H2O is in vapor form that we call water vapor. So the air that consists of neon gas, argon, krypton, carbon dioxide, oxygen, and also nitrogen gas without H2O, this type of air we call dry air. However, the air that consists of numbers of gases such as neon, argon, krypton, carbon dioxide, oxygen, and also nitrogen with water vapor, H2O, or sometimes we call H2O as water vapor or moisture content, and the air with H2O or water vapor or moisture we call atmospheric air. So we have two types of air that we consider for the air conditioning application. Okay, so both type of air we will consider for air conditioning application. And now in air conditioning application, we consider air as a mixture. Okay, so air is a mixture between dry air and also water vapor, where in terms of properties or behavior, the dry air is constant in terms of phase, and throughout the process in air conditioning system, the dry air in terms of phase will be constant as a gas throughout the process. So the phase of the dry air always in a gas form, and also the mass of the dry air also will constant throughout the process in air conditioning system. However, for the water vapor, the properties for the water vapor is not constant, where water vapor during the process of air conditioning system, the phase will change, and also the mass value also will change. So the amount of water vapor inside the air and also the phase of the water inside the air also will change during the process. So these changes depend on the condensation and also evaporation of the water vapor inside the air, where the condensation and also the evaporation process will affect the amount of water vapor inside the air, inside the atmospheric air. And the amount of water vapor inside the atmospheric air will affect the human comfort. Okay, so for human comfort, so we need to have a proper amount of water vapor inside the atmospheric air. So if the water vapor, in terms of amount of water vapor, too high in the atmospheric air, this condition will give uncomfortable condition for the human. And also, if the water vapor amount is very less or very minimum, it will also cause uncomfortable condition for the human. So that's why it is important to provide the suitable amount of water vapor inside the atmospheric air. Okay, so that's why we need to have air conditioning process in order to make sure the suitable amount of water vapor inside the atmospheric air. to make sure that call the comfortable condition for the human. Okay, so that's the difference between dry air and also atmospheric air for the air conditioning application. Air conditioning application. For air conditioning application, in terms of temperature range will be between -10 degrees Celsius to 50 degrees Celsius. So this temperature range actually include the temperature range for cooling process and also the heating process. That's why we have the maximum limit in terms of temperature value up to 50 degrees Celsius, because this value already considered for heating process. Okay, so atmospheric air that we have discussed consists of dry air that represented by A symbol, and also water vapor that represented by italic V symbol. Okay, for dry air, in terms of call behavior, we can consider dry air as ideal gas, where in terms of enthalpy value, if you want to determine the enthalpy value for dry air, we can use the enthalpy change formula, where delta HA for dry air equal to Cp for air multiplied by the temperature difference delta T. So now if we use reference temperature equal to 0 degrees Celsius, we can use this formula to determine what we call the enthalpy for dry air for specific temperature, where HA equal to Cpa multiplied by temperature, specific temperature in degrees Celsius. Okay, so if we look at the table shows the what we call the value of Cp for the dry air for different value of temperature, start from -10 up to 50 degrees Celsius based on the temperature range for the air conditioning application. So we can see the different value of Cp for different value of temperature. So in order to simplify the calculation, we just take the average value of Cp based on the temperature range, where we will get the average temperature from -10 to 50 degrees Celsius, Cpa equal to 1.005 kJ per kg Kelvin, where this value is acceptable because the error of the value is less than 2%. So we can use this value in our calculation to determine the enthalpy value or any formula that involves Cp for dry air. So we can use Cp for dry air equal to 1.005 kJ per kg Kelvin. For water vapor, also we can consider the water vapor for the air conditioning application as an ideal gas, where in order to determine the enthalpy difference, we can use this formula where delta H equal to Cpv, Cp for water or water vapor, multiplied by delta T. So if you look at TV diagram for the water, so we have the saturation line, and we have what we call numbers of constant pressure line as shown in the TS diagram. Start from we can see what we call the value of pressure stated in the TS diagram, start from 0.8 kilopascal up to 5 megapascal. Okay, and then we can see that we have what we call the red color region. So red color region represent the area that we can consider the water as water vapor as the ideal gas. And the green color line or green color curve represent the value the curve for H constant curve. So any point on the same on the same curve of H will have the equal value of H. Okay, so any point on the specific curve for H constant will have the same value of enthalpy. Okay, so if you look at the TV diagram, so the value of PV, if the value of PV below than 10 kilopascal, the value of HV, enthalpy value for water vapor, equal to the value of enthalpy at saturated vapor, Hg. So Hv equal to Hg. So if you look at the TS diagram, let's say we have the condition of Hv in ideal gas region, and at 10 kilopascal the value of Hv will be equal to Hg. Okay, for the pressure below the 10 kilopascal, we can use the relationship in terms of enthalpy, where Hv equal to Hg. Enthalpy for water vapor equal to enthalpy of the water at saturated vapor. However, if we look at the value of what we call pressure for the air conditioning application, the pressure normally is equal to at 1 atm, where the value of 1 atm equal to 101.325 kilopascal, which is approximately the value, if we refer to the TV diagram, is almost equal to 100 kilopascal. So let's say the P total for air conditioning application is around 100 kilopascal. So if we look at TV diagram, at the point in ideal gas region, Hv, the value also close to Hg at 100 kilopascal. So for the air conditioning application, we also can use the value of the relationship of Hv more or less equal to Hg. Okay, so that's why in order to determine enthalpy value for water vapor, we can use saturated water table in order to obtain value of Hg at specific temperature. Let's say we already have the temperature, so we can use saturated water table to determine the Hv value, the enthalpy for water vapor at specific temperature, where the value will be equal to Hg, enthalpy at saturated vapor at specific temperature. Or we can use this formula, where we use 0 degrees Celsius as a reference temperature, use the enthalpy difference equation, where delta H equal to CPV multiplied by delta T. So now, because our reference temperature is 0 degrees Celsius, so just substitute the enthalpy value for 0 degrees Celsius. Now the equation will be Hg at specific temperature minus Hg at 0 degrees Celsius equal to CPV multiplied by T minus 0 degree. And the Cp value is equal to the Cp for water, where the value is equal to 1.82 kJ per kg Kelvin. So now, after we find out the value of Hg at 0 degrees Celsius by using saturated water table, substitute the value of CPV 1.82 kJ per kg Kelvin into the enthalpy difference equation. So we will get the final equation for Hv, where Hv more or less equal to 2500.9 plus 1.82 multiplied by T, temperature in degrees Celsius. So the value of 2500.9 actually the value of Hg at 0 degrees Celsius. So we can use to determine Hv, enthalpy for water vapor, by using saturated water table at specific temperature, or we can use this formula, where Hv, enthalpy for water vapor, equal to 2500.9 plus 1.82 multiplied by temperature in degrees Celsius. And because the atmospheric air we consider as a mixture, the mixture between dry air and also water vapor, so now we can use the mixture equation for the ideal gas. So we can use the formula for ideal gas, where PV equal to RT, and also we can use the total pressure equation for mixture, where P total equal to PA plus PV, partial pressure for dry air plus partial pressure for water vapor. So total pressure will be equal to partial pressure of dry air plus partial pressure of water vapor. Okay, where PA equal to dry air, partial pressure for the dry air, and PV is the partial pressure for the water vapor. Air conditioning properties. Okay, under air conditioning properties, in terms of thermodynamic properties, we discuss the properties such as humidity, temperature, and also enthalpy. For humidity, there are two types of humidity. First, we have specific humidity, and the second one we have relative humidity. As we know, human comfort depends on the amount of water vapor inside the atmospheric air. Thus, the thermodynamic properties that describe the water vapor content in the atmospheric air is referred to the humidity. So first we have specific humidity that represented by omega symbols. So in terms of formula or definition of omega, specific humidity omega equal to mv, water vapor mass, divided by ma, dry air mass. So if we implement what we call the equation for ideal gas, PV equal to mRT, we arrange the equation, so we get M equal to PV divided by RT. So substitute the value of MV and also MA based on this equation. So we will get second equation for omega, where omega equals 0.622 PV divided by PA. Omega equals 0.622 multiplied by partial pressure of water vapor divided by partial pressure of dry air. Okay, the value of 0.622 actually come from the equation of PV mRT. Okay, let's say we consider a room. So inside the room or a confined space, we have water vapor that represented by blue dot, and also dry air that represented by red dot. And when we substitute the equation of PV mRT into omega equation, so we get mV divided by ma equal to RA TA divided by RV TV multiplied by PV VV divided by PA VA. So as we know, in a confined space or in a room, because both dry air and also water vapor we consider as gas, so in terms of volume, the volume of dry air and also what I call the water vapor will occupy the whole volume of the room. So the volume for VA equal to VV equal to V room. Okay, similarly with the temperature. So the temperature for TA will be equal to TV will be equal to T rooms. However, the individual pressure for dry air is not equal to individual pressure of water vapor. Okay, so the term TA divided by TV we can cancel out. Similarly with the term for VV divided by VA. Now we will have MV divided by MA equal to RA divided by RV multiplied by PV divided by PA. So the ratio of RA divided by RV will be equal to 0.622. So that's why we will get the second equation for omega, where omega equals 0.622 multiplied by PV divided by PA. And then if we implement the total pressure of a mixture, where total pressure equal to PA plus PV, substitute into the second omega equation, so we'll get omega equals 0.622 multiplied by PV divided by total pressure minus PV. Okay, and the value of omega actually represent the amount of water vapor or moisture content. So if the value of omega increase, that means the amount of water vapor or moisture content in the atmospheric air also will increase. Okay, the second parameter that you use to describe humidity is the relative humidity, psi. So the relative humidity will represent by the symbol of psi. And this parameter or this this parameter will determine or will describe the comfort level for the air conditioning system. So in terms of definition, psi or relative humidity equal to mV divided by mg. MV stand for mass of water vapor, mg stand for the maximum amount of moisture that air can hold at the same temperature. Okay, so this term actually refers to the saturated condition. For example, if we have a confined space, so inside the confined space we have a cold metal bar, and we have dry air that represented by red dot, and also water vapor that represented by blue dot. So let's say we add more moisture into the confined space. We add more and more until the condition will be saturated, where under the saturated condition we will have water droplet that form on the surface of the cold metal. So at this condition, just after the condensation process occur, the formation of liquid water occur. So the amount of water vapor or water vapor mass at this condition will consider as mg. Okay. So if we implement the same equation of ideal gas PV-MRT for the relative humidity equation, so now we will get psi or relative humidity also equal to PV divided by PG, the partial pressure for water vapor, and also the pressure during the saturated condition. Okay, so in front of the equation we don't have any constant value, because the substance for water vapor and also the Mg is referred to the same substance, which is water vapor. So R value is the same. Okay, so we have same volume, same temperature, and also same value of R. So that's why we have psi or relative humidity equal to PV divided by PG. So the value of relative humidity will be in between 0 to 1. So 0 represents the lower limit, where the value of psi or relative humidity equal to 0 will describe the dry air condition, where no moisture content inside the air. And the value of 1 represents the saturated air condition, where the air is saturated with moisture. If we add more moisture at this condition, the water vapor will condense. The liquid water will form at this condition. Okay, for saturated air condition where the relative humidity value of psi equal to 1, the value of, if we implement to the equation of omega at saturated condition, so omega in terms of PV pressure, PV value is also equal to PG when the saturated air condition occur. So omega equals 0.622. So we replace PV with PG. Omega equals 0.622 PG divided by P, total pressure, minus PG. Okay, where PG is saturated pressure. So we can obtain the saturated pressure by referring to the saturated water table. Okay, so we can find the PG value. If we have the temperature, we can directly obtain the PG from the saturated water table. And if you combine the equation for relative humidity and also specific humidity, we will have another equation that shows or that combine in terms of parameter between omega and also psi. So we have psi equal to omega total multiplied by total pressure divided by 0.622 plus omega multiplied by PG, and omega also equal to 0.622 multiplied by psi multiplied by PG divided by P total minus psi multiplied by PG. So these are the equations that can be used to determine the specific humidity and also relative humidity for air conditioning system application. Okay, next is the total enthalpy for the atmospheric air. So for the atmospheric air, as we know, is a mixture of water vapor and also the dry air. Okay, so in order to determine the total enthalpy for the atmospheric air, the total enthalpy for the atmospheric air H is equal to the enthalpy for dry air plus the enthalpy for water vapor. Okay, so the capital letter of H represent the enthalpy, where the unit will be kilojoule. And in terms of formula, H enthalpy equal to mass multiplied by specific enthalpy H, small letter H. So we have the second equation for the total enthalpy, where total enthalpy equal to mass for dry air multiplied by specific enthalpy for dry air plus mass for water vapor multiplied by specific enthalpy for water vapor. So now if we divide the second equation of total enthalpy with mass of dry air, so we will get the third what we call the total enthalpy equation, which is the total specific enthalpy small h equal to total enthalpy divided by mass of dry air equal to specific enthalpy for dry air plus mv divided by ma multiplied by specific enthalpy for water vapor, also equal to specific enthalpy for dry air plus specific humidity multiplied by specific enthalpy for water vapor. So now the unit for the specific total enthalpy will be kilojoule per kg of dry air, because this equation we already divide by the mass of dry air, so that's why the unit will be kilojoule per kg of dry air. Okay, so we will have the formula for the total specific enthalpy equal to HA plus omega HV, because omega equal to mv divided by ma. As we know, the enthalpy for water vapor, the specific enthalpy for water vapor is more or less equal to the specific enthalpy at saturated vapor at specific temperature or pressure, where we can obtain the value of Hg from the saturated water table, or we can use the equation for Hv that we have learned before. So now instead of we use Hv, so we can use Hg in the equation of total specific enthalpy, where total specific enthalpy H equal to HA, specific enthalpy for dry air, plus omega multiplied by specific enthalpy for the saturated vapor. Okay, so that's the equation that can be used to determine the enthalpy for the atmospheric air. Example 6.1, a 5 meter times 5 meter times 3 meter room contains air at 25 degrees Celsius and 100 kilopascal at a relative humidity of 75%. Determine A, the partial pressure of dry air, B, specific humidity, C, the enthalpy per unit mass of dry air, and D, the masses of the dry air and also the water vapor in the room. So from this question A asks you to determine the value of PA. Question B, you need to determine the value of omega. Question C, you need to determine the value of H total. And the question D, you need to determine the value of MA and also MV. The solution for example 6.1. So first, question A, so you need to determine the partial pressure of dry air, PA. Based on the data given, VA equal to VV equal to V room equal to 75 meter cubic. The room temperature equal to 35 degrees Celsius, also equal to TA and also TV. PA is not equal to PV. Relative humidity already given at 0.75 or 75%. Total pressure equal to 100 kilopascal, where we know that the formula for total pressure equal to PA plus PV equal to 100 kilopascal. And PV value we can determine by using PV formula, where PV equal to relative humidity multiplied by Pg, and PG we can obtain by using the saturated water table, where PG equal to P saturated at 25 degrees Celsius. So based on the saturated water table, at 25 degrees Celsius we can determine the value of P saturated at 25 degrees Celsius, which is equal to 3.169 kilopascal. So from this value we can determine the value of PV, partial pressure of water vapor. Substitute all the value in terms of relative humidity and also P saturated at 25, so we can obtain the value of PV, which is equal to 2.38 kilopascal. And based on the total pressure equation, we arrange the equation so we can determine the equation for PA, where PA equal to 100 kilopascal minus PV. So PV value will be determined, so we can calculate the value of PA, the partial pressure of dry air, where the partial pressure of dry air equal to 97.62 kilopascal. Okay, question B. So you need to determine the specific humidity value omega. As we know, there are many equations involved with omega, so we can choose the most suitable equation for omega based on the data available. So we will use this equation where omega equal to 0.622 multiplied by PV, PV already determined, divided by P total minus PV. Okay, so substitute all the value inside the equation, so you will get the value of omega equal to 0.0152 kilogram H2O divided by kilogram dry air. Question C, the enthalpy per unit mass of dry air. So the data given in the question, VA equal to VV equal to V room equal to 75 meter cubic, TA equal to TV equal to 25 degrees Celsius, PA is not equal to PV, relative humidity equal to 0.75, and P total equal to 100 kilopascal. As we know from previous slide, the equation for total specific enthalpy, H equal to HA plus omega Hg. So now we need to determine, in order to determine the enthalpy per unit mass of dry air, we need to know the value of HA and also the value of Hg. Omega value we already determined from the previous question. So HA can determine by using this formula, where HA equal to Cp multiplied by temperature in degrees Celsius, and Cp value for the air equal to 1.005 kilojoule per kg Celsius. And omega, previously we obtained the value where the omega value is equal to 0.0152 kilogram H2O divided by kilogram dry air. So now let us determine the value of HA, where HA equal to Cp multiplied by T equal to 1.005 multiplied by 25 degrees Celsius. So we will get the value of HA equal to 25.125 kilojoule per kg of dry air. And now, in order to determine the value of Hg, we need to refer to the saturated water table. Okay, based on the temperature, so we already have the temperature for the air is equal to 25. So from the table, at 25 degrees Celsius, we can obtain the value of Hg equal to 2547.2 kilojoule per kg. And then substitute all the value of HA, omega, and then also Hg into the total specific enthalpy equation. So now we will get the total enthalpy per unit mass of dry air will be equal to 63.8 kilojoule per kg dry air. For question D, so we need to determine the mass of dry air and also mass of the water vapor in the room. So by implementing the equation for ideal gas PVMRT, rearrange the formula, so we will get the formula for M equal to PV divided by RT. So for mass of dry air, MA equal to PA multiplied by VA divided by RA multiplied by T. So we have the information for VA, where VA equal to VV equal to V room equal to 75 meter cubic. PA we already determined, which is equal to 97.62 kilopascal, and PV equal to 2.38 kilopascal. So now for this formula, the temperature must be in Kelvin, so you need to convert the temperature from degree Celsius to Kelvin. So you need to add 273, so you will get T equal to 298 Kelvin. The value of RA, the gas constant value for dry air or for air, equal to 0.287 kilopascal meter cubic per kg Kelvin. And the value of RV for water vapor equal to 0.4615 kilopascal meter cubic per kg per Kelvin. So substitute all the value for dry air into the equation for mass for dry air. So we will get MA or mass for dry air equal to 85.61 kilogram. Similarly, for the mass of water vapor, we need to manipulate the same equation. So MV will be equal to PV multiplied by VV divided by RV multiplied by temperature. Or we can use the formula for specific humidity, where MV equal to omega multiplied by MA. So substitute all the value, so you will get MV value equal to 1.30 kilogram. Okay, the next properties for air conditioning system is about the temperatures. So we know that the temperature range for the air conditioning application is between -10 degrees Celsius to 50 degrees Celsius. So there are three types of temperature that we need to consider. First is the dry bulb temperature. The symbol that we use to describe the dry bulb temperature is TDB. And the dry bulb temperature actually the ordinary temperature of atmospheric air. So in order to measure the dry bulb temperature, we just use the typical thermometer. For example, we just take a normal thermometer and measure the temperature of air inside a room. So the temperature that measured by the thermometer is referred to the dry bulb temperature. Okay, the second temperature is the wet bulb temperature that represented by TWB symbol. And this temperature actually is the temperature that measured by a thermometer whose bulb is covered with a cotton wick, saturated with water, and to blow air over the wick, as shown in the schematic diagram. Okay, so actually this temperature shows the saturated temperature at the atmospheric pressure. Okay, the wet bulb temperature is represent the temperature during saturated condition at atmospheric pressure. And the last type of temperature we call dew point temperature, that represented by TDP symbol. So this temperature is the temperature at which condensation begins when the air is cooled at constant pressure. So TDP actually same as the saturated temperature at partial pressure of water vapor, as shown under TS diagram. So TDP actually is same as the saturated temperature at partial pressure of water vapor. And the figure shows the soda can, where we can see that liquid water droplet form on the surface of the wall of the soda can. So this phenomena occur due to the temperature of the soda can wall is less than dew point temperature. So when the temperature of the can wall is less than dew point temperature, so the water vapor that very close to the wall will experience the condensation process, and the water vapor from the air will change into liquid water, and then that's why we will have liquid water droplet form on the surface of the soda can wall, as shown in the figure. So due to the temperature of the wall less than dew point temperature of the air. Okay, where the temperature of the wall less than dew point temperature of the water vapor. Example 6.2. In a cold weather, condensation frequently occurs on the inner surface of the window due to the lower air temperatures near the window surface. Consider a house that contains air at 20 degrees Celsius and 75% relative humidity. At what window temperature will the moisture in the air start condensing on the inner surface of the window? Okay, so from this question, if we draw this quick diagram, so we have a house and we have a window, and the temperature of the air inside the house is 20 degrees Celsius with relative humidity of 75%. Let's say if you draw the what I call the temperature distribution of the air inside the house, so we have the starting point at 20 degrees Celsius. When the air approaching the window surface, the air temperature will reduce, let's say 19 to 19, and then reduce again at 18, 17, until the temperature equal to the window temperature, window surface temperature. So now in this question, the question asks you to determine what is the window surface temperature when the condensation process start to occur at the inner surface of the window. Okay, so that's the question asks you to find out the value of T window, the inner wall temperature of the window when the condensation process occur. Okay, solution for 6.2, example 6.2. At what window temperature will the moisture in the air start condensing on the inner surface of the windows? So in terms of data given, the temperature of the air is at 20 degrees Celsius, relative humidity at 0.75, total pressure equal to atmospheric pressure. Condensation occur when the air reach its dew point temperature. So dew point temperature is equal to the saturated temperature at partial pressure of water vapor, PV. So now we need to determine the value of PV, where PV equal to relative humidity multiplied by PG, and PG is equal to P saturated at 20 degrees Celsius. So P saturated at 20 degrees Celsius we can determine by using the saturated water table. So based on the saturated water table, at temperature of 20, so we can determine the P saturated, where P saturated at 20 degrees Celsius equal to 2.339 kilopascal. Okay, P saturated at 20 degrees Celsius, which is also equal to PG at 20 degrees Celsius, equal to 2.339 kilopascal. And then multiply the value of PG with 0.75, which is relative humidity. So we get the value for PV. PV equal to 0.75 multiplied by 2.339 kilopascal equal to 1.754 kilopascal. Based on the saturated water pressure table, if we refer to the value of PV, which is equal to 1.754 kilopascal, so we need to make interpolation in order to determine the T saturated at PV. So from the interpolation we will get the T saturated at PV, where the value will give you the value of dew point temperature. So the dew point temperature TDP equal to T saturated at 1754 kilopascal, which is equal to 15.4 degrees Celsius. Okay, so if the wall temperature, if the window temperature at the inner surface below than 15.4 degrees Celsius, condensation will occur at the inner surface of the window. If the temperature higher than 15.4 degrees Celsius, no condensation process will occur at the inner surface of the window. Okay, now I will explain about the internal window fogging in a car. Let's say during the raining season, the condensation or the fogging phenomena occur inside inside a car. So let's say the outside temperature is equal to 20 degrees Celsius, and inside temperature, the temperature in the car is 30 degrees Celsius, and with relative humidity of 75%. If we draw the temperature distribution line, So the temperature of air will reduce from 30 degrees Celsius to 27 degrees Celsius to 25 degrees Celsius to 23 degrees Celsius until the temperature of the inner wall of the what I call the front glass of the car, let's say at 21 degrees Celsius. Okay, so let's say the temperature of the front window of the car is 21 degrees Celsius. So now we want to determine whether at this condition the condensation or the fogging phenomena occur or not in the car. So first we need to determine, as we know, the condensation or fogging will occur when the air reach its dew point temperature. So now we need to determine the dew point temperature first in order to determine whether the condensation or fogging phenomena occur inside the car. So for the initial condition, based on the saturated water table, so at 30 degrees Celsius we can determine the P saturated pressure, where P saturated equal to equal to 4.246 kilopascal. So from this value we can determine the value of PV. So P saturated at 30 degrees Celsius equal to Pg at 30 degrees Celsius equal to 4.246 kilopascal. So by using this value we can determine the value of PV, partial pressure for water vapor, equal to relative humidity multiplied by P saturated at 30 degrees Celsius, which is equal to 3.184 kilopascal. From the partial pressure of water vapor, we can determine the dew point temperature based on the same saturated water table, based on pressure. So we need to make interpolation between 3.0 to 4.0 kilopascal, and also the saturated temperature between 4.08 and also 8.96. So by using the interpolation, so we can determine that the dew point temperature, which is also equal to the saturated temperature at 3.184 kilopascal, equal to 24.9 degrees Celsius. Okay, so if we draw TS diagram, so dew point temperature is equal to the saturated temperature at 3.148 kilopascal, at 3.184 kilopascal. So the condition given in the picture, where the temperature is 21 degrees Celsius, is located below than this dew point temperature, which means the condensation or the fogging phenomena occur at the inner surface of the window inside the car. So how to solve the problem, how to eliminate the fogging or the condensation in the car? So let's say we decide to increase the inside temperature of the car, maybe by using a heater. Let's say the inside temperature is equal to 35 degrees Celsius after we use the heater. Now, in order to determine whether by increase the temperature whether the condensation will occur or not, so we need to repeat the process where we need to determine the P saturated at 35 degrees Celsius, which is also equal to Pg at 35 degrees Celsius. Refer to the saturated water table. The value will be P saturated at 35 degrees Celsius equal to 5.628 kilopascal. And then we determine again the new value for partial pressure of water vapor, where PV equal to relative humidity multiplied by P saturated at 35 degrees Celsius equal to 4.221 kilopascal. And then determine the new value of dew point temperature, where dew point temperature equal to T saturated at 4.221 kilopascal equal to 29.8 degrees Celsius. So we can get this value by using the saturated water table through the interpolation. So if we replot at DTS diagram, so we'll get new constant pressure line for PV, where PV equal to 4.221 kilopascal, and the dew point temperature, which is also equal to the T saturated value at PV equal to 4.221 kilopascal at 29.8 degrees Celsius. So compare with the temperature of 21 degrees Celsius, the temperature of the window of the car at the inner surface. So the temperature still below than the dew point temperature. So condensation will still occur, and due to the temperature difference, far a bigger temperature difference compared to the first case, so we'll get more condensation process. Okay, the fogging phenomena become worse compared to the previous one. Okay, so water vapor condensation increase. Let's say now we decide to reduce the temperature inside the car by switch on the air conditioning system in order to increase the air temperature inside the car. Let's say the temperature of the air inside the car reduced to 25 degrees Celsius. Okay, reduced to 25 degrees Celsius. And again, we need to to recalculate the P saturated. So now at the temperature of 25 degrees Celsius, so P saturated at 25 degrees Celsius equal to Pg at 25 degrees Celsius equal to 3.169 kilopascal. So we can obtain this value from the saturated water table. And then again find out the value of PV, the new PV at 25 degrees Celsius, where PV equal to relative humidity multiplied by P saturated at 25 degrees Celsius equal to 2.377 kilopascal. And recalculate the dew point temperature. So now the dew point temperature at 2.377 kilopascal equal to 20.2 degrees Celsius, 20.2 degrees Celsius. So if we plot on the TS diagram, so we'll have new constant pressure line of 2.377 kilopascal, and we have new dew point temperature where the dew point temperature is equal to 20.2 degrees Celsius. So if we compare to the temperature of the inner wall surface of the windows of the car, so the temperature of the inner surface at 21 degrees Celsius is higher than the value of dew point temperature, which is greater than 20.2 degrees Celsius. So now for this condition, the water vapor of the air very close to the wall still remain as water vapor. So no condensation or fogging will occur inside the car. Okay, so that's how the method how to eliminate the fogging or condensation process that occur at the inner surface of the windows inside a car. Okay, how about if the condensation occur at the external side? So I will let you to think and answer the question by yourself. Okay, that's all for this part.